Okay, so what I'm going to do today is give you the introduction to the Lorenz equations. It's sort of a motivation of where it lies in the history of dynamical systems and why we study it. And then tomorrow I'll take a bit of a step back and look at removal problems. But so late in the afternoon it's easier to deal with the context in the videos than the heavy calculations. Right, so the Lorenz equation story starts roughly in the 1960s. Okay, you had this guy working at the MIT Department of Meteorology, and what he wanted to do is they were just at the start when they were looking at how to predict the weather. So predicting the weather is notoriously hard, and what Lorenz did is he basically told us why it is hard, as well as understand in some sense the essence of why it is hard and why it will always be hard. So if you think about the weather, the last time I looked at how weather predictions are made, you basically have 3 or 4 competing huge models of weather predictions in the world where they feed in various amounts of data and they churn it in the supercomputer and then they get answers out, okay? And then if the answers agree, everything is well. If the answers don't agree and there's like an important event like a satellite launch or a war or something like that where the weather becomes like life-changing, what they basically do is they get some of the most experienced, like 3 or 4 of the most experienced weather guys in a room together in the United States, and they all look at the models and they go, I think it's that one. Okay, so there's still an element at the highest point where when the models don't agree, and sometimes they don't agree because of this very feature we're going to look at, that it's still human intuition that is calling what the forecast actually is for crucial decisions. Anyway, our understanding of why the weather is unpredictable came largely or was clearly illustrated by Lorenz. Okay, and so what he did is he took a pretty simple model and he put it on a computer, and we'll actually look at the model. That's what we're going to study. In fact, just to give him full credit, the paper he wrote on this model is readable. If you actually wanted to go and read a good scientific first paper, you should read it by the paper Lorenz did. In fact, a lot of the analysis that we're going to do after the test and after the break comes directly from the paper. It's a beautiful analysis that he did. So if you want a classical paper to use as a model, go and have a look. Okay, so what he did is he noticed the problem. So at that point, it was like 1963 or so, computers weren't strongly developed. I think they were still working with punch cards, which basically meant you had a whole bunch of cards with holes in them to put your data into the computer, and then they had a whole bunch of things that read the cards, read the thing in, and it turned out an answer. And it couldn't work like today. We work to 16-digit accurately, easily all the time. My computer, I even push to 32 digits if I really care about the answer, and they were having fewer digits. And what Lorenz noticed was that the computer would spit out an answer, and it would be accurate to say like 8 digits or so. And then one day he fed in the thing, but he lost one of the digits. And he'd actually repeated the calculation. The previous day he fed in the same initial conditions, but with a few more digits. And that spat out an answer. And then the day after that, he started the same thing, but he truncated a couple of the digits, and it spat out a vastly different answer. And then, like any good computer science, he went to debugging. He wanted to know why, if I simply made a round of error, did I have these very large mistakes? And initially, he said, well, okay, clearly the program's wrong. So he checked the program, clearly I made some other mistake. You check that. I got the equations wrong. I made a typo in my code. And every time it's a very expensive question because it's not like sitting at a keyboard and telling the software what to do. It was literally programming things with these cards. So you get to punch your cards or whatever. And eventually he realized that it was none of those things. The answer he was getting out was right. And he went about trying to explain why just 1 or 2 digits at the end made such a huge difference. And in that explanation, he discovered what we call now a strange attractor. It's an inherent unpredictability that arises in deterministic equations. So no quantum mechanics, nothing like that. It's fully deterministic equations, and there's an unpredictability factor built in, And the mechanism by which this occurs is what we're going to study. Okay, so he literally was the father of chaos theory. And he had discovered what we call a butterfly effect. I don't know if you've ever heard of the story that you have a butterfly that flaps its wings somewhere, and this little thing causes a little vortex, and eventually you have a tornado going. It's sort of the idea that you can have a tiny, small thing that makes a difference that has a huge, drastic consequence. It's kind of like the guy that leaves a screw in a jet engine and blows up a plane. You know, things like that, where you can have dramatic consequences from a very, very small change. And he showed that in the equations that he was studying, this was exactly how they worked. Okay, so he discovered what we call deterministic chaos. In other words, deterministic meaning we have the differential equations that are straightforward differential equations, ODEs, that totally determine the future of your system at a state. And in spite of that, you have chaos. Okay, you have unpredictability. So it's not as if we've got noise or anything else pushing into the system. The system itself becomes unpredictable. And I kind of like this quote. Lorenz is less known. I'm sure you've heard of like Schrödinger and Bohr and the people that started quantum mechanics. And then you've always heard of Einstein that started the relativity. But this guy actually, Emmanuel Carey, put it well. He said, by showing that certain deterministic systems have formal limits, basically Ed Lorenz put the last nail in the coffin of the Cartesian universe and fomented what some have called the third scientific revolution in the 20th century, following on the heels of relativity and quantum mechanics. Okay, so the Cartesian universe, when people started mathematics like Descartes, and so they had this dream that everything could be structured and ordered and you could understand from first principles the laws that governed the universe. And systematically that picture has failed in the sense that inside a system you cannot always predict what is coming, even if you have all the information. And the first way it failed was basically with relativity, this idea that you have one body pushing the other one. Einstein showed instead that you have a nonlinear effect and you have to solve the Einstein field equations, and you have black holes where you can't get any information out. So their determinism also kind of went. Then it was quantum mechanics, where the idea was that the world that we thought of particles colliding, in essence, at its lowest level, that doesn't exist. There are probability clouds as we now understand them. Might not be the complete understanding, but it's literally the fact that all things we see are made from unseen things rather than concrete little balls that knock against each other. So it's a shift in our understanding of what it was. Also, when we had Newtonian mechanics, we had this idea that it was a universe. You set it going, and then you understand exactly what's going to come afterwards if you have the right differential equations. And what Lorenz did is he killed that hope, in some sense, that even if you know the differential equations exactly, like we're going to show, and the equations can be quite simple, you still cannot predict what the solution is going to be like infinitely far ahead of time. And this type of chaos is inherent in the systems we see in our weather. So I want to give you an idea of what Lorenz was studying. So where his equations came from was a simplified model for convection rolls. So what a convection roll is if you put like two metal sheets. Okay, you make one hot at the bottom and one cold. If the two are the same temperature, the fluid does nothing. If you start heating the bottom, initially nothing's going to happen as well. It's just going to stay stationary. But at some point, some parts of the fluid get so light they want to go up. Exactly. And then they go to the top, they cool down, and they fall again. And then so your stationary state of fluid starts having these rolls coming up. And these are convection rolls. And we see them a lot in the atmosphere, like very often, like the huge clouds we get, they are actually a giant convection roll governing it. Very high in the atmosphere, you see these little cirrus clouds that are tiny little convection rolls that are going there. So we see it all around us. And one of the models, in fact, for the patterns on the zebra and some of the other things is that in the embryo, you have a small little convection roll that sets on the pigments, and then you get these patterns forming. And so basically these convection rolls, this is just the side view, and this is the edge-on view. They extend in the medium, and once you heat a certain temperature, you start seeing these rolls. And people have actually videoed these rolls, and the way they video the rolls is literally you have a see-through sheet, like I think it's a sapphire crystal, basically, or some crystal at the bottom and a crystal at the top, and you can heat it and you can shine light through it. And when you do that, when the rolls start moving, there's a different density in the liquid that goes up as opposed to the liquid that's coming down, and that acts as a lens. And so if you shine light through it, you can actually see the rolls themselves. And so when you go beyond, so what typically happens, initially the temperature is the same, there's nothing, you switch the temperature on, and you start forming long lines of rolls like that. And if you increase the temperature even further, these long lines of rolls actually break up into patterns. Okay, so you've seen a bifurcation diagram that we've seen with reasonably simple systems. There are very, very complicated bifurcation diagrams that people have been working out for, in this case, it's liquid helium that's trapped. In other cases, what they've also studied is liquid crystals. And there's a lot of research happening in the spirit of Germany and Bayreuth on actually imaging these things because it has applications for our computer screens. Okay, so the equations that you map out when you understand convection and eventually how liquid crystals react to heat and electricity and makes these things is useful for making computer screens. So these things actually move. So here's a video of what these convection rolls actually look like in time, okay? And depending on how the temperature is, these patterns actually change. So for a low temperature, you just have straight lines. As the temperature goes up, those straight lines start breaking, and eventually you have structure forming in the system. And now I must just find a way of killing this. Okay, so that particular thing is called spiral defect chaos in Rayleigh-Bénard convection, and it's an example of a convection roll. And this is even still more complicated than what Lorenz was studying. Okay, here's just another example. What also influences is the shape in which the convection roll actually is. So this is just another example of what can happen. So patterns very similar to patterns we see all around us, but we never really notice them. And it's formed just by the gradient in temperature and the convection roll starting out, and the fluid equations. Okay, so that's some very basic controlled convection experiments with liquid helium in the lab. What Lorenz did was even simpler, but you can see some of the technology that happens. So one of the things that Lorenz did, and that was known slightly even before Lorenz, is that the way deterministic chaos starts is that you can have two solutions that start initially very, very similarly, and then within a certain period of time, they depart exponentially. And that feature is called the sensitive dependence of initial conditions. So it's just introducing the concepts we're going to look at much more concrete detail when we start looking at the Lorenz system. But kind of these videos are useful for illustrating to you what you should be expecting and what you in fact are describing when you start doing the mathematics and you start getting stuck in the Jacobians and all things like that. So what this one is, it's an example. It's actually Steve Strogatz doing the model. It's also, I just kept it for historic purposes because I kind of like having the course that he made with the videos that he used. So this is a lab experiment of a double pendulum. So we've done the single pendulum that we saw, and we saw the driven single pendulum earlier today. This is simply one solid pendulum, and then over here it has another pivot, and there's a second pendulum. Okay, and so you have to describe the motion of this branch and the second branch separately, and so you have more equations than just two. Instead, you have four, and then you can also have chaos. And what this video does, it illustrates very well what a sensitive dependence of initial conditions are, and it gives you old Steve Strogatz's voice and his kind of sometimes goofy way of going about things.
This is Steve Strogatz again. Now we're at Howard Stone's office at Harvard in sciences at Pierce Hall. We're here to demonstrate the motion of the delta pendulum, which is one of the standard beautiful examples of a nearly conservative system that shows Hamiltonian chaos. So the first thing is the familiar solutions from freshman physics, like this, the small amplitude solutions, which look like normal mode motion. There's that. Or we could also start in a mode something like this, where they're in the antiphase. But a much more interesting thing to do is to start a solution in the full nonlinear regime, let's say like so. Now watch this now. That's remarkable. And eventually damping has its way. Now, you'll notice that solution I started like this. I could start a solution with the same initial energy, like so. If you think this one will be more or less interesting to watch. So this example shows that it's not just the energy that determines the dynamical complexity of the motion. Another thing we can show is what's known as sensitive dependence on initial conditions, and that can be seen by looking at two different solutions, or two different pendulums. They've actually made two nearly identical pendulums. So let's start them the same, and let's see how long their motions stay together. Not very long. This is Steve Strogatz.
Okay, so there are a number of things that you could notice there. The first one is, even if you have a chaotic system, not all initial conditions result in chaotic motion. There are still regions in the system where it's highly predictable. And this is a Hamiltonian system, so it basically has four equations. The Lorenz equations we're going to see is only a 3, so it's actually not a Hamiltonian example of chaos. It's even simpler than the system. This one is just nice because it's a very clear, intuitive feel for how you can have one answer for two identical systems, and then with a very short period of time, if you started in the right initial conditions, it's going to depart very dramatically from each other. Okay. And that rate of departure we often characterize with what we call the Lyapunov exponent, how rapidly the two solutions move basically apart. Okay, so now what I'm going to do is, I don't want to start it yet. I'm going to show you another video of Strogatz. So this has to do with the Lorenz equations. So we are not actually going to derive the full Lorenz equations that Lorenz used. Instead, we're going to derive a simpler version because it's somewhat easier to do the derivation, and there's a very clear intuitive model for how we build it up. So we're actually going to derive the Lorenz equations in a particular subcase in full generality that you can see how the things build up, and that's why I need to do the Fourier transform stuff in greater detail the next time. So the case or the model that's entirely analogous, that results in exactly the same equation as the Lorenz equation, is a model that models the motion of a water wheel. And so what this video does, it actually just gives you a picture of the actual apparatus that was built, that you have a very clear picture of how we actually start doing the derivation when we get to it. It's also, once again, I think this is when he was in theoretical applied mechanics, but let's have a look at this, and then I'll say a little bit more about the Lorenz equations afterwards. Let's just get it going. It's funky.
show about the Malkus water wheel designed and built by Malkus at MIT. I'm Steve Strogatz. I'll be doing most of the narration here and how it's going to work the video camera. Now, first let me show you a little about this water wheel. Alright, if I turn it on, then you'll see that water comes out and goes into many chambers around the rim of the wheel. This manifold pumps the water. The water is pumped up through here, comes out through these nozzles into these chambers. And notice that the chambers have little holes in them, and that's why the water comes out. By the way, the water has been colored green with food coloring so you can see it. Now, let me show you some solutions here, some of the behavior of this wheel. First, well, I have two control parameters I can play with. One is I could turn this screw, which would prop the wheel up more, and that would effectively change gravity. The other is that there's a brake here, which I can tighten or loosen, which changes the coefficient of rotational friction. So let me now just set the brake in a certain place and show you a particular type of behavior. With any luck, this will settle into a uniformly rotating solution. Okay, now there was nothing special about rotating in that direction. Notice that everything is symmetrical. The water is coming in symmetrically at the top, unlike a normal water wheel where water would come in on the side. So I should be able to get it to rotate in this direction too, in a steady way and uniform way. And it seems like that's more or less happening. True? Yeah. Okay, Howard believes it. But now let me change the parameters to one where those parameters were such that this uniform rotating solution was stable. But that's not always the case. Now if I tighten the brake a little bit to here, I should be able to see a complicated motion in which there are reversals, irregular and unpredictable reversals of the wheel. Okay, so far it's just rotating to the right.
Still not uniformly.
Certainly not uniformly. And now it's gone back to the left. Let's see, will it go to the right? Now it goes to the right. Well, now it's going to go to the right again. Nope, it goes back to the left.
You're right there.
Ah, yes. All right. Can we ever get it to go twice in the same direction? Has it done that yet? Oh, no.
Did at the very beginning.
At the beginning, maybe. Come on, go over the top.
Next time, Phil. Not quite.
I made it too tight.
Yeah.
I mean, give it one more. One more? You see, if the brake is set too tight, it goes into a simpler motion, which is just a once to the left, once to the right, once to the left, once to the left, once to the right. So we were hoping to get a chaotic solution as a regular reversal. Maybe I can get that by loosening it a little bit.
Went twice before.
Yeah, but and there it goes twice in that direction. Okay, this is better.
Now, you might want to mention some mechanical analog.
Well, yes, this is a mechanical analog for the famous chaotic system known as the Lorenz system, discovered by Professor Lorenz also at MIT in the 60s. To see the analog, roughly, physically speaking, you can think of the wheel as single convection cell, and the rotation of the wheel is like the rotation of the convection cell. The difference, though, is that the driving here is the water inflow, whereas in the convection problem it's temperature gradients. Actually, this is an exact analog, and for a derivation of that connection, you can look at chapter on the Lorenz equation. Well, okay, that's the office water.
Yeah, okay, thanks. So a couple of things. Did you see the number of people that were on the initial video? Generally, research in the US and successful groups are done by a group of people where each guy or person or woman does their part, and then you can actually get further than individuals would go on their own. Another feature is it wasn't a fancy lab in some sense. It was. I was always, when I went to Cornell University the first time, we do physics, and we had this lab that they call 510, which is notorious. It's the only course you had to do when you did physics, and the people that did theory always weren't very fond of it. But you had all the classical early experiments, and I thought, thinking, oh, this is a good university in the US, I'm going to get all this fancy equipment, and I was surprised at how old the stuff was. It was simply used, and people knew how to use it well, and it illustrated some basic physical concepts. So I actually ended up enjoying it, despite the fact I can be quite clumsy. So that's the other observation. The next thing is, it wasn't really a complicated system, right? A lot of truths and things can be illustrated with a very simple system, and that's what Lorenz actually did when he derived equations. He basically took something that he didn't understand, that he initially thought was a bug in his code, and he understood it in such detail that he pushed forward our understanding of what strange attractors are. And so the final video I'm going to show you is just a simulation of the Lorenz attractor itself, of the equation. So you can simply think of it as a trajectory in three-dimensional space of a particle moving around the convection rolls. And you can see what behavior is possible with a strange attractor, and what it would look like if you were to have a system in which two solutions you could start infinitely close together, and within a finite time they have vastly different answers. And let's just get it. Let's just not run, Mr. Okay, so here we go. So this is the Lorenz attractor. Over here on the side is a whole bunch of parameters, and we'll start understanding what the parameters are when we actually derive the equations. But needless to say, just like the case with the sensitive dependence on initial conditions with a dumbbell pendulum, you have situations where you can start at a certain type of initial data and parameters, and you go to a fixed point and you stay there. And part of the detective story that Lorenz did was to basically exclude all those possibilities, and basically said, I have nothing else. I've got to go to this strange thing that doesn't behave like anything else anybody has ever seen before. That said, too, it was a discovery that was guided by the fact that he could integrate the equations. Right, up until before the computer was really starting to be developed for the atomic bomb things, people did not have the benefit of actually seeing the solutions. Every single analysis was being done by perturbation theory. And so you can see why that sometimes you will actually not see certain features of the equation if you just do it that way. And so the advent of the computer, even though a simulation only gives you one answer, it gives you an idea of guessing at the analysis, or at least an annoyance enough to try and describe the results that you actually come out with concrete mathematics. So here is a very nice synergy between getting a numerical answer and then pushing fundamental mathematics of dynamical systems further. So let's just have a look at how the attractor behaves. So it goes and has an unstable spiral, it spirals out until it reaches a maximum, and then it does something else, loops back. Do you want to watch it again, or that's enough? The video is on the internet, or sorry, on the website, so you can take a look at it there if you do want to see it again. Okay, so a structure unlike you've most probably seen before. There's a lot of mysteries over there. If you look, it seems to spiral out around, where is it? Oh, there's the mouse. Okay, it seems to spiral out around 2 holes over here. And we actually do the analysis, those are unstable fixed points. And then it sort of randomly hops from one area to another area. And then another feature is it seems to be stuck on roughly a surface. But part of the problem is that it's impossible that it's stuck on a surface. So Lorenz actually made that argument, it can't be a surface because of the uniqueness theorem. So it's stuck on something else with a fractal dimension. And what Lorenz did, he broke several, he basically invented several things in his paper, which makes it such an unusual paper. But basically the idea that you could have something running on a fractal surface and view that as an attractor was not done before. What he also did is, just like the Poincare map, he made a Lorenz map. Similar idea to try and get some handle on how to analyze a thing, and that was also not done before. And in doing so, he actually connected dynamics with, once again, a discrete map, and put at the disposal of the people that were analyzing these things a whole bunch of new tools. Okay. So the computer glitch or the error led him to looking for answers, and he came up with some very, very good ones. So I think that might actually be all I want to say. Just while the video of the water wheel is still fresh in your minds, I just want to sort of look at the structure, and then we'll actually go on the deriving of the equations of that actually after the break. So just to remind you what the water wheel did, if we look at it from the top, it had that black pipe. Okay, and so what was happening, you basically had the black pipe pumping water into a whole bunch of chambers all the way around here, like those little squares in the water wheel where the liquid went in is a whole bunch of separate chambers, and at the bottom of each one of those chambers were little holes where the water actually leaked out. Okay, and that particular water wheel, just to give us the time, it was built in the 1970s by Marcus and Howard at MIT. So the equations Lorenz derived in like 1963, and then people struggled to understand it even after his paper, and then they came up with this mechanical analog that has exactly the same equations. Okay, and so the top view, you basically have that with the jets, and you have it in the black arm, and then what happens is the water comes in, these chambers fill out, and then they leak out at the little dots, and you can have this whole system rotating freely along the axes. And then what you do is you have basically tilted this water wheel at an angle, and you spray the water in at the top. So eventually you spray the water in, it kind of gets heavy, and we'll do this in greater detail, and then it starts to spin around to the left or to the right. And the thing that we actually measure when we do the Lorenz equation is you have a laser or a sensor that actually measures whether it's rotating left, rotating right, and how fast it's rotating. And so that is what we're going to be modeling. And so when you actually do record the case where it's in a chaotic state, typically you have it that it spins, like oscillates like this, and then it goes round, and then it oscillates in the other direction, and it spins over, and then it oscillates in one way, and then it clicks over and spins and oscillates in the other way. So that's basically just how they were actually recording their observations of their mechanical system. Okay. And so just have that sort of more concrete picture along with a video sort of in mind for next semester stuff. Any questions about this at this point? Okay. So let me stop the recording here for the other guys.